Mr. Heffernan here, and here's a video on the greenhouse effects. Alright, so our atmosphere has approximately a mass of 5.15 times 10 to the 15 tons, which is approximately 0.000086% of the Earth's total mass. Yeah, it's not very much, but it's compared to some planets, it's a lot. Like Mars has practically no atmosphere, but does have something, but not very much. Weather and most life exists in the troposphere. So for the Earth, we've got some different areas. We've got the atmosphere, which is all the air or gases of the planet. We have the hydrosphere, which is the water and liquids. And then we have the lithosphere, which is the solid parts. And then we have all the living parts, which is the biosphere. Now, just in the atmosphere, you have the troposphere, which is anywhere from 0 to 12 to 18 kilometers in height. That's where you find all the mountains, all the weather, and all the animals. I mean, you could maybe have some bacteria up in the higher atmosphere or far down below somewhere else, but generally most of the life is right here. Once you go above breathable air, you're in the stratosphere, anywhere from 11 to 50 kilometers. And then you get into the mesosphere, okay, and then you get into the thermosphere, which has got an extreme change in temperature. It goes from like minus 86 degrees to 1200 degrees Celsius. And then you go to the exosphere, outer space, basically, where if you're in direct sunlight, it can be very hot, and if you're not, it can be extremely cold. Alright, so the atmosphere is mainly made out of nitrogen, oxygen, and other chemicals. Nitrogen makes up 78% of the Earth's atmosphere. Oxygen is about 21%. Water vapor can vary, but it can be up to around 2% of the atmosphere. And then argon, carbon dioxide, etc. make up almost 1% of the rest of the atmosphere. So here we got the atmosphere, hydrosphere, lithosphere, and biosphere again. Okay. The Earth's atmosphere has changed over the billions of years, but generally speaking, it's been pretty stable for a while now. So if you want to compare other planets to see what kind of atmospheres they have, you can look at this graphic down here. Okay, you can just pause the video or download this slideshow and take a look at this one. Okay, so one of the important chemicals we have is ozone, or O3. O2 is what we usually breathe. O3 is actually bad for your lungs. Okay, smells very sweet though. And where we do need this is up in the stratosphere. In the stratosphere, we need ozone. Provides us protection against ultraviolet radiation from the sun. So it'll block things like UVC, which are very damaging. The UV A and B's. Some of the B will get through, but just being in your car, the window will block most of that, or your clothes will block it, and you get your UVA as well. We actually do need ultraviolet radiation with vitamin D for your body, keeps you healthy. Okay. So about I guess since the 1940s or 50s, we were using chemicals called CFCs for refrigeration. Unfortunately, we throw the old refrigerators and freezers and air conditioners out. These chemicals would go into the atmosphere and take out the ozone. And ozone is usually made from lightning going through the sky. And unfortunately, this opened up some holes in the ozone layer, and we were getting extra ultraviolet radiation. And skin cancer rates were going up for people and for animals as well. So the world governments came together and signed a protocol in Montreal, and actually as of last year, I think 2019, 2018, scientists noticed that the ozone hole is actually starting to repair itself. So this international work is working. Now, pollution from auto exhaust, etc., can cause ground level ozone. It's a huge health risk for people, especially if you have emphysema or asthma. Now, solar radiation. Over 99.9% of the Earth's energy comes from sunlight. Even hydrocarbon energy like oil and gas and coal came from trees that grew using sunlight through photosynthesis. And then when the trees died and were buried underground for a long period of time, they converted into coal and oil. So sunlight comes from nuclear fusion in the sun's core. Our sun is a star. Its name is Sol. That's why we live in the solar system. The fusion core is around 15 million degrees Celsius. And by the time you get to the surface of the sun, which is really large, it's down to about 6,000 degrees Celsius. And you can see the different parts of the sun here. You got your chromosphere, your photosphere, the nuclear fusion in the core. So nuclear fusion is basically a couple of hydrogen atoms come together and eventually form a helium atom. And that's what nuclear fusion is. So the sun is mostly made out of hydrogen. And most of the universe is hydrogen. Okay, solar radiation. So the sun emits its radiation. It gives off some electrons, which is called beta radiation. Helium ions, which are called alpha radiation, and they get blocked by the Earth's magnetic field. That allows us to have technology. Otherwise our power grids would be overloaded all the time. You wouldn't have a cell phone. And then we get our electromagnetic, which people just call gamma radiation. So that's like the ultraviolet, etc. There's infrared. That's like 51% of it. You can't see it. It's just a little bit below red on the spectrum. You get your visible spectrum: red, orange, yellow, green, blue, indigo, and violet. It's 47%. And then ultraviolet's around 2%. About 54% of the radiation hits the ground. 86% is trapped in the world and eventually radiates out into space. Greenhouse gases is what traps this thermal energy and keeps the planet warm. So there you go. Here's the spectrum of light that we get. This is what happens. 23% is absorbed, 29% reflected, 54% reaches the Earth, and then that gets radiated off and then gets reflected back down or absorbed, and that's what happens. So the greenhouse effects, from studying greenhouses, people know this is how it works. So the Earth's atmosphere is similar to a greenhouse. It allows visible light to enter and then traps it, the infrared light inside, warming it up. Okay, it's just the simple physics. Without the greenhouse effect, the Earth would cool down to an average temperature of minus 18 degrees Celsius. Kind of like Mars. Mars is very cold. You just can't keep the heat. So the atmosphere is too thin. So here's some extreme pictures right here, like New York being frozen. And actually one time, it's odd, the Earth actually was a snowball planet at one point in time. Luckily for us, things warmed up. So here's the greenhouse gases that we use to keep warm. Carbon dioxide is the one that you always hear about, or carbon. Before the Industrial Revolution, there was 280 parts per million, and that was the highest it would ever get during its fluctuations for a few 100,000 years. This says 365 ppm when this chart was made, but we're well over that. We're past 410 now. When it gets into the atmosphere, it can last anywhere from 50 to 200 years, and its global warming potential is 1. Methane gas used to be 0.7 parts per million, now it's over 1.7 parts per million, so we've more than doubled it, getting close to tripling. And it lasts in the atmosphere for about 12 years, but it has 23 times more effect on global warming compared to a carbon dioxide molecule. Then you got your nitrous oxide. We've only increased the nitrous oxide a little bit by 50%. It lasts 114 years, and it's like 296 carbon atoms when you put one of those in. And then you got your parafluorine methanes, CF3, and you've got your sulfur hexafluorine. But, well, basically most of our emissions in 2018 were carbon dioxide, 81%. That's why we mainly focus on that and the methane, which is 10%. In fact, it's actually better to burn methane than it is to let it go. As you can see, it's got a global warming potential of 23, and when you burn a methane, so you take some methane, add a couple of oxygen and burn it, it makes a carbon dioxide and a couple of water molecules. So it's actually better to burn methane than to let it escape. Okay, so here's some of the greenhouse gases. Sulfur hexafluorine. And if you want to take a look, you can take a look at this graphic that talks about where we use it and how it's been affecting the atmosphere. But it's not one of the big ones. Okay, but we make it basically from ozone depleting refrigerants, substitutes for CFC, sorry, and industrial processes that make aluminum and semiconductors. Nitrous oxide, also known as laughing gas, mainly comes from agriculture, industrial processes, also used by dentists and street racers. Kind of looks like this molecule right here. Okay, NOS. Methane, this is one of the two big ones. So CH4. Methane comes from a lot of human activities, such as leaks from natural gas systems, raising of livestock, and it's also emitted from some natural sources like natural wetlands. 30% of the world's methane comes from natural sources, 40% from agriculture, and 30% from other sources. Cows are one of the worst ones, actually. They ferment the food in their stomach, and by chewing their cud, they're constantly giving off methane. Some fools want to put masks on the cows to trap it, but it's like, you imagine how inhumane that would be. Okay, so carbon dioxide is the big one. It's the one that's caused the most global warming and climate change. And it comes from human activities burning hydrocarbons, or fossil fuels, which we just call carbon now, oil, gas, and coal. We've been burning a lot of hydrocarbons since the beginning of the Industrial Revolution in 1750, and it's just accelerated, right, every year. Where we use it: transportation, electricity, industry, residential uses, and other uses. Alright, so if you take a look at carbon dioxide emissions, you can see at the beginning of the Industrial Revolution, we weren't emitting that much. Even by 1800, not much. 1850, starting to pick up a bit. 1900, and then you can see the exponential growth here for our emissions as more and more countries become developed. If you take a look, you can see the United States, one of the big emitters, same with China, and you got India, you got Europe and Russia. Canada, pretty big emitter for its size, same with Mexico. Okay. So as emissions have grown exponentially, and Europe and the USA actually slow down, Asia's been picking up and making up the difference. So, if you take a look at Canada in particular here, Canada has 0.5% of the world's population, with 37.3 million in 2018. Our economy, though, makes up just over 2% of the world's economy. So that means on average we're doubling the average person in the world with 4.16% for 1% population. And if you look at our carbon emissions, we make 1.6% of the world's emissions. And that's triple the average person on the planet, with 3.2% of the emissions for 1% of the population. So here's the different economies right here. So the first attempt at slowing down the emissions was the Kyoto Protocol, and we'll get into this in our next video.